Let us evaluate the integral 0 to pi log of 1 plus a cos x by cos x dx by using the technique of differentiation under the sign of integration. This technique is also called Feynman's technique. Observe that if I change the value of a, then the integral changes. So we call this to be a function of a and we denote it by ia. Now we will apply the technique of differentiation under the sign of integration. So let's differentiate both sides with respect to a. So d dA. How about the right hand side? The technique says that, well, if you differentiate and then integrate, or if you integrate and then differentiate, the result will be the same. However, we got two variables a and x, so we differentiate partially with respect to a. We differentiate partially with respect to a. Okay, so far so good. Now, if I differentiate log with respect to a, we know that d du of log u is 1 by u, so it is 1 by 1 plus a cos x. And then differentiation of a cos x with respect to a, that is simply cos x, because derivative of a with respect to a is just 1. Now we are regarding cos x to be a constant as we regard x to be a constant when we are differentiating partially with respect to a. So cos x is just a constant. We can cancel cos x out, right? Yeah, let's cancel it out. When we cancel cos x, we got a much simpler expression. Of course, integration is from 0 to pi. Now, how do we integrate such an expression? We know that cos x equal to 1 minus tan square x by 2 divided by 1 plus tan square x by 2. So we let t equal to tan x by 2 and differentiate both sides with respect to x. We are letting t equal to tan x by 2 and we are differentiating both sides with respect to x. Derivative of tan is sec square x by 2, derivative of tan x by 2 is sec square x by 2, and then we should differentiate x by 2 as well, so we get half, and sec square is 1 plus tan square, but we are assuming t equal to tan square, so 1 plus t square times half. So we can write dx equal to 2 by 1 plus t square dt. Okay, when x equal to 0, t is also equal to 0. When x equal to 0, t equal to 0. When x equal to pi, t approaches tan pi by 2, tan 90 degrees undefined, so t approaches infinity. So we can say that di dA is exactly equal to integral 0 to infinity. As t changes from as x changes from 0 to pi, t changes from 0 to infinity. 1 by 1 plus a, we got cos x equal to 1 minus t square by 1 plus t square, 1 minus t square by 1 plus t square, and then dx equal to 2 by 1 plus t square dt. Alright, we can cancel 1 plus t square out, and so we will be left out with 2 is just a constant, so we need not write, we can write it outside the integral. When we multiply by 1 plus t square, we get 1 plus t square plus a minus a t square dt. Can we integrate it? Yes. So we got di dA equal to 2 times integral 0 to infinity 1 plus a plus 1 minus a times t square dt. We take 1 minus a common. So the integral 0 to infinity 1 by 1 plus a by 1 minus a plus t square dt. We assume mod a to be less than 1. This is simply undefined for a equal to 1. And if I take mod a less than 1, this quantity remains positive. And so we can write it as square root of this expression, whole thing square. Now we know the formula 1 by a square plus x square dx. Integral of 1 by a square plus x square dx is 1 by a. A is simply root over 1 plus a by 1 minus a, tan inverse of t by a. So t by root over 1 plus a by 1 minus a. Of course, we need to change t from 0 to infinity. That's equal to 2 by 1 minus a. When we tend t to infinity, as we take larger and larger value of t, tan inverse of t will turn out to be pi by 2. 1 by root over 1 plus a, 1 minus a, we copy as it is, minus when I take t equal to 0, tan inverse of 0 is simply 0. Now we can cancel root over 1 minus a, and so we'll be left out with root over 1 minus a times root over 1 plus a, that is root over 1 minus a square. So you got di dA equal to 2 by root over 1 minus a square. So opposite of derivative is integration, so we integrate it and say that I equal to 2 times integral of 1 by root over 1 minus a square dA, and that's simply equal to integration 1 by a square minus x square dx, that is sine inverse of x by a, in this case a by 1. Of course, plus some constant of integration. So you got IA equal to this. Let's write IA equal to, let's recall IA equal to integral 0 to pi log of 1 plus a cos x divided by cos x dx. Clearly, I0, we want to somehow compute this constant, I0 equal to 0 to pi, log of 1 is 0 dx is simply 0. So you can say 0 equal to sine inverse of 0 is 0 plus constant, that implies constant equal to 0. So IA turns out to be 2 times sine inverse of A. No constant.